Welcome everybody to this week's community Zoom for the Green Bank Observatory. I'm Jim Jackson, I'm the director. Still a brief update on what's happening in Green Bank. So winter is upon us. We've had our first snowfall. There's a little bit of flurries in the air now, but we continue to observe. Back to normal operations. The observatory went through its annual program review from the NSF last week. We had a nice panel review the function of the observatory and how we performed in the past year and our plans moving forward. And I thought that went very well. So kudos to the team here who worked so hard to make those presentations. And I thank the NSF and the panel for spending the time to look at what we're doing and to provide some important feedback. Just to let you know, the special call for proposals is due at the end of the week, at the beginning of next week. Not sure the exact date, but we did have the supplemental call. If you're interested in using the low frequency receivers and have large programs, this would be a good time to get your proposals in. So without any further ado, I'll pass it off to Jay Lockman, who will introduce this week's speaker.
Okay, thanks. Our speaker today is Eleonora Bianchi from the University of Grenoble, and she'll be speaking about the early stages of solar-type protostars, the missing evidence of large carbon chains. If you have questions, you can submit them using the Q&A box in the lower right of your screen. Thank you.
Thanks a lot for the introduction. So I start to share my screen. Okay, so hello everyone. And first of all, I would like to thank the organizers to give me the opportunity to be here. I'm Eleonora Bianchi from the University of Grenoble, France. And I'm very happy to share with you some results we obtained thanks to the GBT observations. I would like to thank all the people involved in the project. And I will talk to you about astrochemistry, in particular about complex carbon species in the early stages of solar-like protostars. So first of all, why we are interested in investigating these complex carbon species? Well, when we observed prestellar cores and protostellar sources, means systems information that will become similar to our solar system, we see basically two different types of chemistry. One is the hot Corino chemistry, with emission lines from oxygen-bearing species and the so-called interstellar complex organic molecules. And the other one is the warm carbon chain chemistry sources, where we observe unsaturated hydrocarbons and carbon chains. One hypothesis for the origin of this difference is the difference in the collapse timescale, which could favor chemical reactions starting from CO or, in the case of WCCC, methane, CH4. So in general, CH4 is formed through hydrogenation of neutral carbon, and in typical molecular cloud, neutral carbon is rare because of the efficient formation of CO. However, when the transition from the diffuse cloud to the molecular cloud is very fast, a substantial fraction of carbon can freeze out into the dust grain mantles before the CO formation. So the presence of such a W carbon chain chemistry zone may be a signature of fast collapse. Alternatively, if the source is embedded in a relatively thin cloud, CO photodissociation can play a role and lead to a large amount of methane. So we need more observation to clarify the origin of this chemical diversity and also to explore the complex carbon species reservoir, which is mainly unknown so far. We know that there are simple carbon chains such as CCH, for example, in the inner 100 AU region around protostars, like in the case of this source, 1527, where we observe this ring at the interface between the infalling envelope and the Keplerian disk, so in the so-called centrifugal barrier region. So we want to observe more sources, and the project I'm going to present you is part of a community observational effort to explore the chemical content of star-forming regions at different wavelengths. So this effort started in 2009 with the large program CHESS in the infrared, and then it goes on with several large programs in the sub-millimeter, such as ASI, which is astrochemical survey at IRAM 30 meter, or the Calypso survey with the Plato-Debut interferometer. The SOLIS project for NOEMA, which is Seeds of Life in Space. FAUST, which is an ALMA large program which stands for 50 AU study of the chemistry in the disk envelope system of solar-like protostars. And now we are focusing on radio wavelengths with this project with the GBT, and in the future using Ska and GVLA. So there are two main reasons for that. The first one is that at millimeter wavelengths, dust opacity can prevent us from detecting molecular emission, while its effects are expected to be less severe in the radio. And this is important for young embedded sources. And also because if we want to observe large molecules, we need to go at lower frequency, where there is the peak of emission. And so the project I present you consists of a pilot project of 53 hours in total observed with the GBT. And it was observed in two parts. So the first step was a survey of the KU band between 13.9 and 15.4 gigahertz of two objects, L1544, which is the prototype of a prestellar core, and IRA 1629-2422, which is the prototype of a sun-like protostar. Both objects are very well studied in the sub-millimeter, and they show a rich chemistry with emission lines from relatively simple carbon chain species, cyanopolyeins, and interstellar complex organic molecules. Given the spectra of L1544 were particularly rich in the KU band, we decided to follow up this project with a survey also in the X band, so between 8 and 12 gigahertz. And these are the first results. So the analysis is in progress, but you can already see that we detect many molecular species, and that the spectra of the two objects show significant differences. So in particular, in IRA 1629-3, we detected this C3H emission from the envelope parental cloud and formaldehyde from the protostar, while in L1544, the prestellar core, we detected many species, so these carbon chains, C4H, C6H, many cyanopolyeins lines, and sulfur-bearing species. And I want to stress that we are sampling the emission at large scales, but in the case of IRA 1629-3, even if the emission from the compact sources can suffer from beam dilution, we are targeting the extended envelope. So the large scale envelope fills the GBT beam. So these observations are telling us that there is a real chemical difference between these two regions. And the first step of this analysis, we focus on the cyanopolyeins emission in L1544. And here I show you some bright emission lines from HC3N and HC5N. So in particular, we have one rotational transition and two rotational transition, respectively, for the two species, with several satellite lines due to the hyperfine splitting. And bright emission lines from HC7N and HC9N. HC11N is not detected, but we could derive an upper limit. And so the first message is that L1544 hosts a complex carbon chain chemistry. And in the case of these two species, we have enough transitions to perform a rotational diagram analysis in order to derive the emitting gas properties. So you see here the main results. We perform a rotational diagram analysis assuming local thermodynamic equilibrium and optically thin lines. Unfortunately, we do not have the information about the spatial distribution, so we assume as a first step that the emission fills the smaller GBT beam, which is around 54 seconds, and we obtain a rotational temperature around 4-5 Kelvin and column densities between 1.6 times 10 to the 12 to 8 10 to the 13 centimeters to the minus 2 from HC9N to HC3N. And we also derive the upper limit for HC11N. And here I show you the comparison between the abundances of these cyanopolyines measured in L1544 and the other measurements obtained towards TMC1, which is a prestellar core in Taurus known to be very chemically rich. And it is nice to see that we obtain a similar trend in the cyanopolyines abundances. Our upper limit for the HC11N is not so stringent to see really any deviation from this trend, but this can be further investigated, for example, using spectral line stacking technique, as done before for TMC1, to verify if also in L1544 we see a different behavior here with respect to the other cyanopolyines. The next step we are working on is the chemical modeling to try to reproduce the observed abundances. And in any case, these first results are important because they show that a rich carbon chemistry is ongoing also in L1544, and it may be common also in other sources. So indeed, in the last few years, a huge effort has been done to explore these carbon chains and rings in star-forming regions. In particular, TMC1 has been the target of the Gotham and the Quixote survey with the Green Bank telescope and the Yebes 40 meters. And these surveys have revealed a new chemical complexity with the detection of several species for the first time in the ESM. And you see here some examples. And also the ARCAM survey performed with the GBT had observation in other 4 sources. And it seems to show that this complex chemistry is widespread and it is not well explained by the current chemical models. So our observations are important to start to do comparisons between the chemistry of the different sources in order to investigate the complex carbon species formation processes. So to summarize, we surveyed with the GBT L1544 a prototypical prestellar core and IRA 16293, a prototype of a protostar. We are sampling the large spatial scales. We do see differences in the chemistry between these two sources. And we do not really understand which is the reason. We need to investigate what can be the main reason for this difference. And the main limitation of these studies is that with the GBT, we cannot investigate the compact emission coming from the inner regions of sunlight protostars. So in the next years, we will have NGVLA and Ska, which are two new facilities that will revolutionize this kind of study, allowing us to explore the small spatial scales. And I will show you briefly this Ska user case, which was inspired by this GBT pilot project and that was developed in the framework of the Grenoble of Life working group. And the idea is the exploration of EV carbon species in a star-forming region, which we think is representative of our solar system birth environment, studying it at high angular resolution. So we propose to target OMC2 because the large Ska beam will cover several protostellar regions, including the OMC2 FIR4 protocluster, which is particularly interesting for its chemistry. And we propose observation to target the inner 200 astronomical unit. And the region has the advantage of being very well studied in the submillimeter. So we have also an idea of the energetic particle flux in the different parts of the region. So this will allow us not only to detect for the first time these complex carbon species around the protostars, but also to investigate their formation and destruction mechanism. And of course, this kind of study will highly benefit from the unique combination of angular resolution and sensitivity provided by the NGVLA, which will allow to observe really the planet formation region. So stay tuned for many exciting results to come in the near future. And thanks a lot for listening.
Thank you very much for a most interesting presentation.
Thank you.
Let me remind the audience to submit questions through the Q&A box on the lower right. And I see that we already have one. Could you speculate on the potential existence or production of PAHs in these star-forming regions?
I'm not an expert of this, and I'm not really a chemist. I'm more on the observational side. I can say that until now, for this complex species, the more formation pathways was thought to be the bottom-up formation, so from simple species increasing the complexity, while in the last year, the top-down formation as becoming also a second possibility, and there are several projects investigating this. So it is not excluded, and we will see. I think we will know more in the near future.
I have a rather technical question, and it's about your SKA proposal,
Yes.
which has a velocity resolution of 1.9 kilometers a second.
Yes.
Is that going to be sufficient for most of these molecules?
But of course, when we ask for, we have to do every time compromise between the sensitivity, angular resolution, spectral resolution to try to have the better sensitivity possible. And let's say that the idea is to target the region near the protostar. So in a hot Corino region, we expect that the line width is typically of the order of 4 or 5 kilometers per second. So 1.9 kilometers per second should be fine. While for the prestellar core, we see narrow lines. But around the protostar, we expect a larger full width at maximum, so it should be okay.
And another question on some of the spectra you showed appeared to have multiple components, multiple kinematic components.
In the GBT spectra, you mean?
Yes.
It's a possibility. It's a possibility. Of course, we don't have the information on the spatial distribution, but maybe we can try to do a non-LT large velocity gradient analysis. And we don't have the collisional coefficient for the more complex species such as HC7N or HC9N. We can try to use the lines we have of HC5N to do this non-LT analysis, and this in principle can give us some information on about the emitting size.
Mm-hmm. We have a comment from Claudio Codella. The superspectral resolution provided by GBT is allowing us to finally probe kinematics. I guess that doesn't need an answer. Any other questions at this point? I'd like to remind everyone that this webinar is being recorded, and in a couple of days it will be uploaded to our website. So you'll be able to watch it and share the link with your friends and any other colleagues. Well, if there are no further questions, let me thank our speaker again, Dr. Bianchi, and remind everyone that our next in these sessions will be on Wednesday, December 22nd. We will have some pulsar results from Haley Wall of West Virginia University, analyzing the NanoGrav 12.5-year data set for information on polarimetry and Faraday rotation measures. Thank you very much for attending, and goodbye.
Thanks a lot. Bye.